Hi there. Today's discussion is about continued discussion on dimensional analysis. The subject we're going to discuss about is modes and the number of particles. Throughout human history, we developed a lot of alternative counting units. And as you learn in elementary school, we have the basic counting units is 1, 2, 3, 4, 5, and each unit is a digit. It's a 1. Then you follow the previous digits. But over the years, we are developing a lot of the kind of substitute because we're dealing with repetitive numbers. For instance, we have 2 hands, we have 2 feet, and a lot of times, the socks is going to come in, always come in 2. The gloves always going to come in 2. So we can have so people over the years start calling it a pair. So a pair of socks, 2 socks. A pair of gloves, 2 gloves. So one pair of anything is equivalent to 2 of anything. So this is just a very simple example, and then a lot of people is buying a unit of 12, in this case 12 eggs, and as you know, it's going to be called a dozen eggs, a dozen roses, or a dozen donuts. So it's like we don't want to talk about the multiples of 12, then we just start talking about dozen. In this case, 1 dozen of anything is equal to 12 individual units of anything. And then we continue to see those alternative counting units. And one of the very interesting thing is baker's dozen, and it turns out baker's dozen, if you count all those donuts on here, is actually 13, and it's 1 baker's dozen equals 1 baker's dozen of anything equals to 13 individual units of the same thing. If you really want to, you may be intrigued now why baker's dozen equals 13. Google it, and there is a very interesting historical aspect to it. The other thing is bushels. Bushels, you see that a lot heard in the news. What's the cost of the corn, a bushel of corn, a bushel of soybean, a bushel of wheat. Those are commonly used on the commodity markets, and essentially 1 U.S. bushel is approximately 35.2 liters. This is about 1 bushel, it's about 35 liters. But how is those going to be translated into actually pounds or kilograms of the particular commodity you are selling or people are buying? Here's a website and actually listed for grains. Barley is about 1 bushel, is about 48 pounds, and corn, if you have complete corn, is about 70 pounds. Cotton is about 32 pounds, and also the fruits and vegetables, they are equivalent mass in pounds, or weight in pounds. In this case, we use it interchangeably. So then let's switch back. And obviously the one everybody heard on a daily basis through the news will be the price of a barrel of oil, barrel of petroleum. And 1 fluid barrel is approximately equal to 119.2 liters. 119.2 liters. As you can see, the list goes on and on and on for alternative counting units. It's for the convenience, and it's mainly for the convenience, and by substituting the basic units out, it's a lot easier to conduct daily businesses. So in these cases, in this podcast, a very important concept is going to be introduced is actually the parallel alternative counting units in chemistry. Before I introduce that concept, I would like to give you a little mental exercise, or is a mental demonstration. So here's a picture of a softball. Nice. It's fairly big. You can put it in your hands, you can touch it, and you can actually see solidly that is one softball. If you start looking at golf ball here, much smaller size. So it's like, if I want to have a tangible feel for it, I better have multiple of it. In this case, you have 3 put in your hand. Pretty much the same feeling as you have a softball. And now you're looking at a marble, and the marble ball is going to be another step. It's just much slower than the golf ball. So if I really want to have that feel, then I need a lot more marble balls. And same logic goes here. If I have a pile of grain of rice, if I really want to have a tangible feel of that, I have to add a lot more. And in this case, it's going to be maybe hundreds, maybe thousands. Just follow the logic along. If I go to the sand, the pile of sand, and if I want to have a similar tangible feel of that, the actually number of grains of sand will increase dramatically. So as the superpancreas says, as the size of the particles decreases, and the number of particles has to increase in order to get to a sample that is tangible. So follow on that logic. As we're getting, the particle size is getting smaller and smaller, and we're going to get to the atoms, the molecules, or the ions. And here's a little bit, give you a little bit of animation, give you a little bit of feel of that. Is on my homepage, and you can actually start with this. It's called Scale of the Universe, and you've done it before. This is a normal one. We actually, in our world, kind of we can feel about it. So then this is actually getting wrong direction. This is getting bigger and bigger. So we gotta switch to the other one, and now we're getting smaller and smaller, as you can give you the sense. And let's drag all the way down to the molecules. So it's about 10 to the negative 10th, and we're going to this is the carbon atom, and this is the structures. This is the structures. Okay? This is the structures. Those are the tiny scale we're talking about. And just want to give you a sense of that. You can actually come back and play it over and over again. So as we continue the discussion, as we say it, as the size decreases, the number of particles has to increases, because we are dramatically further pushing to smaller and smaller particles. So that particular number has to increase dramatically. And that leads into the concept of the mole. Here's a little picture of a lovely mole that lives underground, but that's not the mole we are referring to. And the mole, what we're calling here, is essentially alternative counting units in chemistry. So it's 1 mole of any substance or anything, we call it A, will be equal to 6.022 times 10 to the 23rd particles, individual unit of the A. And first, just one thing is I really want to emphasize, the mole concept in chemistry is no different. It's absolutely no different on the conceptual basis with a dozen of anything equals 12 individual units of that thing. So it's the same. The reason why this number is so big is because of the smaller size. It's the extreme small sizes of molecules, atoms, and ions. As we said, clearly demonstrate as the size is getting smaller and smaller, the number has to increase exponentially. It's getting bigger and bigger in order we can actually have a sample, we can have a touch it and measure it. So with this equivalency or equals, so we can actually come up with two conversion factors now, and in this case 1 mole of A is divided by 6.022 times 10 to the 23rd. Oh, there's a mistake. It should be to the power of 23rd, to the power of 23rd, and this one is also to the power of 23rd. And let me pause and fix that problem. We're back, and let's get the animation show starts again, and we went all through that. Now the conversion factors in correct format is 1 mole of A divided by 6.022 times 10 to the 23rd. Particles of A equals 1, or you can reverse that. 6.022 times 10 to the 23rd particles of A divided by 1 mole of A equals 1. And here comes advice, a piece of advice. Please follow this format. Use the parenthesis, and within a parenthesis is the designation or explanation of what substances or what entity we're referring to. Let's pause, have some fun, and have some fun with that, what we call it, this one, 6.022 times 10 to the 23rd, is called Avogadro's number. This one is called Avogadro's number, and take a look at, give you a little bit of physical sense, the meaning of how big that number is, If we stack 1 mole of paper, one piece on top of each other, and that stack is that can reach the moon more than 80 billion times. You can travel in the back and forth on it 80 billion times. 1 more grain of sand would be more than all of the sand on Miami Beach. Shocking, isn't it? And 1 mole of blood cells would be more than the total number of blood cells found in every human on Earth. More than that, much more than that. And very interesting, 1 liter bottle of water containing 55.5 moles of water. And this gives you a sense of how small the water molecules are. If you're talking about the mole of the little animals, there are 3 types of moles that live on the ground in North America: eastern mole, hairy-tailed mole, and star-nosed mole. Coming back to actually the alternative counting unit, 1 mole of interest would be about this many light years, or across our galaxy and back 8 times. Okay, 8 times is 1,616,434 light years. 1 mole of seconds is about 19 quadrillion years. It's more than 4 million times the age of the Earth, or 954,000 times the age of the universe itself. Ouch. And do we wish we have a 1 mole of pennies that could repay the United States national debt this many times? Okay, let's solve some problems with the mole concept. And in this case, the question is how many hydrogen molecules are there in 0.456 moles of hydrogen gas. So the question asked is how many hydrogen molecules, and what has been given? The moles of hydrogen gas, and you say hydrogen gas is composed of hydrogen molecules. So what you start with is 0.456 moles of hydrogen gas. Hydrogen gas. Remember the diatomic elements is always H2. We can start with that. That will be bringing the conversion factors. In this case, 1 mole of hydrogen gas is equal to 6.022 times 10 to the 23rd molecules of H2. And now you can see the unit cancel each other out. We can have the target unit of molecules or hydrogen molecules, and just carry out, finish the math, and bravo, and you are there. You have the correct answer. Or if you're good at it, and you can use a simpler protocol. And this is what we call it the monkey bar. And you started with 0.456 moles of hydrogen gas, and you write those bar. You start with this. What you want to get is molecules of hydrogen, molecules of H2, and you know this is not the unit you want, so you have to cancel it. So put it on the bottom. Then you say, oh, I know I can actually fill in the blanks with 1 mole of a hydrogen gas will have 6.022 times 10 to the 23rd molecules of hydrogen. And very, very importantly, as you can see, this part is a conversion factor, and it is exactly 1. Now you can see the mole of hydrogen gas, it will be cancelled, and you'll be left with the correct molecules of hydrogen. So then you can carry out the math. It will end up with the answer was 2.75 times 10 to the 23rd molecules of H2. And a little comment on the sig figs, significant figures. You start with 3. All the others are considered to have infinite number of significant figures, so the answer should have 3 significant figures, hence the 2.75. In this case, we used the units to drive the mathematics, and I tend to like this approach because I don't have to remember or memorize. Should I multiply or should I divide? Okay, so let's take a look at example number 2. In this case, we want to know how many moles of water in 7.83 times 10 to the 24 molecules of water. So you started with molecules of water, H2O, and as you can see, the format I use always utilizing the parentheses to specify what you're referring to. And this time I'm just directly going to jump to the monkey bar, and you start with this molecule of H2O. You want to get to mole of H2O, so you have to cancel the molecules of H2O, put it on the bottom, then you simply fill in the blanks. 1 mole of water equals to 6.022 times 10 to the 23rd molecules of water. Molecules of water cancelled, you got your desired mole of H2O. So then you can just simply clean up and carry out the mathematical operations. So you can get this answer: 1.30 times 10 to the 1st molecules of it should be H2O. And let me pause, fix this problem again. We're back, and let's continue the broadcast. So the now is correct with the correct information in the parentheses, and the use of the factor labeling approach will enable you to kind of really solve those problems very efficiently. So with that, I'm ending the broadcast regarding the mole and the number of particles. To summarize, introduce in this broadcast, the alternative counting units in chemistry was introduced. The mole concept, the 1 mole of anything equals 6.022 times 10 to the 23rd individual particles, individual unit of the same thing. And it's very, very important that you use the parentheses to specify which substances is described. And with that, I'm wrapping up this vocast. Please refer to the relevant worksheet to practice. Thank you very much for your attention.